Log on, tune in, find out. Another good idea from Cambridge.
Welcome again to another seminar, and again this is meant to be, I hope, fairly informal, work in progress stuff that's happening here, so I'm sure Heiko will be happy to take questions. I'm afraid I have to remind you as always that because of the recording equipment, if you have a mobile phone on you, please switch it completely off. We did that did work on Tuesday. We didn't have any of the usual interruptions at all, so I think everybody must have taken that to heart and switched their phones off. So I'm delighted to introduce Heiko Grossmann. Of course, he doesn't need introducing, you all know him by now. And I'm really looking forward to what he has to tell us about automatic analysis of variance for orthogonal block structures. Okay, for those of you who, as I said, people would come in after we started. For those of you who've just come in, please switch off your phones. Heiko.
Okay, thank you, Rosemary. Yeah, I'm very grateful for the opportunity to give this seminar today, and I want to thank the organizers and the Newton Institute for that. And what I will be presenting today is some work I've been doing while being here, and it's about the analysis of variance. And you may wonder what the word automatic in the title might mean, but I hope I will be able to explain that during the talk. So basically what we're going to have is actually 4 sections. So I will start off with some introduction, then talk a bit about theory, and then the main thing I want to present today is actually a new sort of program for doing the automatic analysis of variance, which I have called automatic ANOVA. And then to illustrate how that works, we will be looking at several examples. Now, introduction. So let me start with a statement probably everyone here would subscribe to. Every statistician knows how to do the analysis of variance. Okay, so I believe that is probably true, but sometimes the way we learn and teach the ANOVA is centered about specific models. So we have a sort of template approach. If you have this and that model, do this. If you have another model, do something related but different. Now, if we look, however, at more complicated ANOVA models, and by that I mean models which involve a more complicated blocking structure and which may include fixed effects as well as random effects, then it may not be as clear to everyone how to do the analysis of variance in this situation. Now that is basically a statement about statisticians. When doing that work, what I also had in mind were our customers, people actually coming to statistician to ask for some advice. And those people, they do get some training in the ANOVA, but usually only for specific models. So I think usually they are familiar with one-way and two-way ANOVA models for completely randomized designs. But when the situation is more complicated, they do not know as much about that. On the other hand, when they are doing experiments, they usually come up with something which is much more complicated than those simple one-way and two-way models. So there's a discrepancy between their training and what is required for their research. Notwithstanding, when designing their experiments themselves, they may have a good intuition of how to arrange the setup, how to design it, and so that should not be, I believe, undervalued. The other thing we as statisticians are familiar with is that usually customers do not seek input from us at the design stage, but usually show up, for instance, with a data set, and that often takes the form of an Excel file. So the starting point for what I want to do in a sense was actually to do something that would help those customers to do appropriate analysis of variance. So here I have an introductory example, which is a very simple one, and that is taken from Rosemary's book. And it is just a little more complicated than one-way, two-way models. So we have here a situation where we have an orchard with trees. So we have 6 blocks, each of which contains 5 trees. Then we have 2 sorts of treatments. We have 3 sprays. So those are applied to entire blocks with replication 2. So each spray applied to 2 blocks. And then we have another factor, 5 different pruning methods, and they are all used within each block. And then we have a response for that. Now the question is, what is the correct analysis of variance? Now for our customer, that may already be difficult to answer, because that is somewhat probably outside the sort of model that was covered in the training. But also, although everyone here, I assume, can do the analysis for that model, if we ask people, how would you approach that, how would you explain it, then we would probably get different answers. And I think there is, in my perception, a sort of divide between the UK and what I've called here the rest of the world, in the sense that they approach the problem from a different perspective. So here in the UK, and I've also put Australia because Chris is here, there is an emphasis on what is called the plot or block structure, which is distinguished from the treatment structure. Whereas in the rest of the world, the emphasis is on writing down the model equation and then using the general linear model or general linear mixed model to analyze, to actually analyze the data. Now, just a few comments about what I refer to as the UK perspective. So there are 2 influential papers by Nelder from 1965, which deal with the ANOVA for simple orthogonal block structures, that is, for those block structures which can be obtained by iterated crossing and nesting of factors. So that theory was further generalized by Rosemary and other people, and the account of that work, of that generalization I'm using very heavily here in that talk, is basically a chapter in Rosemary's book on comparative experiments. Now, the only software I'm aware which actually tries to follow this, say, Nelder-Bailey philosophy appears to be GenStat. But, and there I come back to my divide, all of the above I think is hardly known outside the UK. And that has resulted in a slow take-up of that theory. And I can only say, when I came to Queen Mary and was assigned to teach a course of design of experiments, I got the lecture notes from Rosemary, and I looked at them and I thought, oh, I've never seen that before.
Well, you say hardly known, it doesn't mean that it is not known, and there are places where it is known, outside UK and Australia.
Yeah, of course I'm exaggerating here. Okay, so...
Do you know which one?
Sorry?
Do you know which one?
Yeah, heard something in Eastern Europe, perhaps?
That's right, in Poznan.
Okay. So what is the goal of this talk? So my goal here is today to present and illustrate the use of a program which I call the automatic ANOVA package. And what this done is it actually implements the approach in Rosemary's book in what I hope a very user-friendly and nice way. So to advertise the package, so I've tried to write down some of its features. So first, what it does is this package provides only a single function to be used, and that function can deal with any orthogonal design as defined by Rosemary. Now, because those words orthogonal and balance and so on are overused in the literature, I tried to put always the references to make clear what I'm actually referring to. So that's orthogonal designs in the sense of Rosemary. So single function, so that covers a very, very large class of designs and models, but of course not everything. Now, because I had this customer in mind, the package requires only minimal input. And what I mean by that is actually an Excel file containing some columns for some factors, and I will show an example later on. And then what you need to specify is actually which columns, so you just enumerate the column numbers, which columns correspond to the plot factors and which columns correspond to the treatment factors. So just a list of column numbers for the plot factors and the treatment factors, but nothing else. And of course, if it is available, a response variable, but the program can also do many things without actually having a response variable, so prior to doing the experiment. Now, and I think that is the most important bit of what I refer to as automatic and ANOVA, is that the program from a list of some factors automatically deduces the appropriate model and carries out the analysis. And that may sound like magic. In particular, it does not require any sort of model formula. For instance, in GenStat, where you have to define a formula for the treatment structure and the plot structure using, for instance, the crossing and nesting operators, something similar is not needed here. What does the program then produce? It automatically gives you what is called, and I need to explain that later on, the null analysis of variance, the skeleton analysis of variance. So these can be obtained even if you have no data, and it gives you a full ANOVA if you have data. It also produces some diagrams, some graphics, which are very important in Rosemary's approach, and they really aid in understanding. So Hasse diagrams, we get one for the plot factors and one for the treatment factors. We also get estimates of variance components, either numerically, or if no data are available, you get the program generates algebraic formula for the variance components. It automatically eliminates redundant factors which are aliased or confounded. It automatically acts pseudo factors if needed, and deals with situations where there are 0 degrees of freedom for some terms. So that's basically what the package can do. Now we come to the theory. So the whole package is based entirely on chapter 10 in Rosemary's book. So that's only a read of 30 pages, which gives you the full theory. Now, because of the divide I've mentioned before, I do not believe that, say, more than 50% of the people here in the room are familiar with the Nelder-Bailey approach. So for that reason, I'm going to run quickly through the theory, but of course that is too much material to digest, so please, in a sense, try to regard it only as a sort of set of pointers where to look at, because it will probably not be possible to understand everything in a short amount of time. So what I'm trying to do is to give a very brief summary of chapter 10 in Bailey 2008. And in all of that, there's not a single contribution from me. So there is only Actually, this whole section 2 is just a single quote. But nevertheless, because there are some concepts one needs to understand, I will try to illustrate that a little bit. So, factors and a relation, which is called the final relation between factors, what the infimum and supremum of two factors is, what actually the Hasse diagram is, and then three structures, or two structures, and one notion of design, orthogonal plot structures, orthogonal treatment structures, and orthogonal designs, and also null ANOVA and skeleton ANOVA terms I have mentioned before in the list of features of the program. Now, even if you get lost at some point in this section, here I try to give a summary of what the approach does on a single slide. That involves terms to be defined later, so I'm not sure how helpful that is. So what we're doing is actually, we're supposing that we're doing an ANOVA experiment and we have n observational units and a corresponding response vector y. Now, we distinguish between between the plot structure and the treatment structure. And if we have an orthogonal plot structure as defined by Rosemary, which we denote here by this curly f, so that is a list of factors, this gives us the decomposition of the space in which our vector of observation lies, the n vector of real numbers, the n space of n vectors of real numbers, into mutually orthogonal other vector spaces where there is one vector space WF associated with each factor in this orthogonal plot structure F. And also, if we look at the square length of the response vector because of this mutual orthogonality, then that can also be written as a sum of sums of squares for the factors in our orthogonal plot structure. Now the second bit is the orthogonal treatment structure. Again, denoted here by curly G, this is a set of factors, but now about the treatments, and this gives another set of mutually orthogonal subspaces of n space. Now if we assume that our plot factors have random effects, and if we also make a specific assumption about the form of the variance-covariance matrix for our responses, which is not very restrictive, then those W spaces coming here from the plot structure are the eigenspaces of the variance-covariance matrix. And then if on top of that we have an orthogonal design, then the analysis of variance is easy because we can test the effect of a treatment factor in a unique stratum or eigenspace of the covariance matrix, which depends only on the plot factors. So that, in a sense, in a nutshell, is what the approach does. Now, so as I said, this section is a big quote, so I'm just trying to mention some of the elements of the theory which are needed. So we start out with a set of n observational units, and this, because I'm adhering here to Rosemary's theory, is denoted by capital omega, and a set curly T of treatments in experiments. So we have the distinction between plots and treatments right at the start. We have factors on both sets, and each factor is just a function into a finite set. So the plot factor has a finite number of levels, the treatment factor has also a finite number of levels, but the plot factors are defined on the set of observational units omega, and the treatment factors on the set of treatments curly T. with every factor f, so let's look at a plot factor first, we can associate the f class for one of its levels I, and that's just the set of all observational units which have the same level I of this factor f. In other words, this is just the inverse image of the level I under the factor regarded as a function. And we can do a similar thing for the treatment factors, but now a class for a level of a treatment factor is the subset of the set of treatments. So for level J, it's all those treatments which are assigned by G the level J. So that means basically that if we look at all the levels of a factor and go back to all the classes, we can talk about a factor equivalently only in terms of its classes. So a factor can be regarded just as the set of all of its classes. Now, we now move on to define the final relation. Now, first, if we look at two factors which are defined on the same set, although their levels may have different names, if their sets of classes are the same, then we call those factors equivalent. Now, moving on, the factor f is said to be finer than a factor g, defined on the same set, if every class of f is a subset of a class of G. And that is, if you think about ANOVA from a different perspective, this final relation is expressing nesting of factors. Now we introduce, so we say here a factor f is finer than G if every f class is a subset of a G class, but the two factors are not equivalent. If, and we use then this symbol here, precedes f precedes G, for indicating the final relationship. Of course, we can also talk about a factor being coarser, G coarser than f, that is when exactly when f is finer than G. And we also may consider the case where f is finer or equivalent to a factor G. Now, what is quite important for the theory and also for the package is the notion of the infima, and I've just copied the definitions again. And what you should at this stage perhaps only look at is the textual bit here, not the formal equivalent of those definitions. So we have, if we have two factors on the same set, then the infimum of the factor, of the two factors f and g, is the coarsest factor, which is finer than the two. And we have also what is called the supremum, and that is the finest factor that is coarser than the two. So that is similar to concepts. For me, it looks most similar to the supremum and the infimum of a sequence of numbers. So this is the largest lower bound in a sense, and this is the least upper bound. And these symbols here, these are important to bear in mind because we will look at them throughout. So that's the infimum, that's the supremum. So for reasons we will see later, there's also two particular factors are singled out, and they exist both on the set of observational units omega and on the set of treatments. We have a universal factor u, which gives the same value 1 here to every observational unit if we talk about omega. And then we have the equivalence factor E, which takes for every little omega and capital omega just omega. So that's in a sense a sort of identity mapping. Okay. Now, the reason for introducing this final relationship and also this notion of infima and suprema is that then they may help to picture the situation in an experiment by means of what is called a Hasse diagram. And if we look at the relation here, finer than or equivalent to, on a set of inequivalent factors, then that's a partial order, meaning reflexive, antisymmetric, and transitive. And that can be represented by a Hasse diagram. And what this Hasse diagram does is to represent a structure. So we can draw up one Hasse diagram for the plot structure and one for the treatment structure. So for the plot structure, or equally for the treatment structure, so suppose we have here a set of inequivalent factors, curly f. Then for each factor in this set of factors, we draw a dot. Now, if for 2 of the factors in the curly f, f is finer than g, then we basically put a dot for f below a dot for g and join them by a line, and there may be some other dots in between. If our curly f contains the universal factor, we put it at the top. If it contains the equivalence factor, we put it at the bottom. Now, in addition to that, we may look at the infima and suprema. So if the supremum of 2 factors is in our set curly f, if of the 2 factors f and g neither is finer than the other, then we basically put an element in the graph which looks like that, so a dot above f and g, and then join it with f and g, and if the infimum is included, we put a dot below and join it to f and g. And next to each factor, we write its number of levels. Now, for instance, in the introductory example, we had 6 blocks, and no other plot factor explicitly mentioned. So as we will see later on, in this case, we would usually include, for the plot factors, we would usually include u, and we would include e, and then we have only blocks, and the equivalence factor is always finer than any other factor, and any other factor is always finer than the universal factor. So here we put the number of levels, and next to the factors, so u has only a single level, we had 6 blocks, and we had 6 blocks of size 5, so in total 30 observational units. So that would be the very simple Hasse diagram for the introductory example. Now, this slide here is not to be read at all, because what it does is, with every factor we can associate a vector space, a subspace of the vectors of n, length n, which has the same value whenever 2, say, observational units are in the same class of the factor. And the reason for putting up the slide here is in Rothenberg's theory, there is a specific definition of orthogonality, and there is also a theorem which helps checking orthogonality. So we do not go into the details of that definition, but the theorem here is actually something I implement for the orthogonality check in the package. Now basically, up to this point, we have introduced some terms, and now we're going to see how this helps the analysis of variance. And that is based on mainly one theorem, and this theorem is the one here. If we have again a set of inequivalent factors, that may be on the set of treatments, or it may be a set on the set of plots. We suppose that whenever two factors are in our set of factors, then the supremum is as well, and that any two factors in curly F are orthogonal to each other in the sense of the definition we have just seen. And then basically the theorem gives us the decomposition we are used to in the analysis of variance. So we can define for every factor a second vector space, basically by taking the sum of the V spaces for factors that are coarser than F, and then take its orthogonal complement within the V space for the factor F. We denote the dimension of those W spaces by dF. And then, if the factors are different, then the corresponding W spaces are orthogonal to each other. If we consider any vector in curly F, then its V space is the orthogonal direct sum of the W spaces for factors G coarser than or equal to the specific factor F under investigation. And if the equality factor is included in our set of factors, then this gives us a decomposition of the whole space within which our observations lie into mutually exclusive orthogonal subspaces, one for each factor. And that also, and related to that, is also an equation for the dimensions of the W spaces here. So the W for a factor F in our set curly F, the dimension of WF is equal to the number of levels of the factor F minus the dg's for all factors G that are coarser than F. And the relevance of that is that basically this bit here about the dimensions gives us the degrees of freedom in the analysis of variance, as we will see later on. And also this decomposition of the spaces into mutually orthogonal subspaces allow us to calculate sums of squares by simply applying Pythagoras' theorem. So if we want to talk about ANOVA, we want to talk about sums of squares, then we can actually talk about first so-called crude sum of squares. So what do we do there? We take the observation vector, project it orthogonally on the VF space, and take the squared length. So that's the crude sum of squares for the factor. And if we project instead the data vector onto the W space for the factor F, square its length, then we get the sum of squares. And the previous theorem also tells us that sums of squares for a factor can be obtained from the crude sum of square for F minus the sum of all the sums of squares for factors that are coarser than the factor F we're interested in. And that is basically the reason why we can use Hasse diagrams to calculate, on the one hand, degrees of freedom for the ANOVA, and on the other, sums of squares for the ANOVA. So what we do is that when we're doing calculations of degrees of freedom, so we will always assume that the universal factor is in our set curly F. Then we start at the top of the diagram. There is no factor coarser than U, so there's nothing to subtract, so we write the degrees of freedom here. So 1 degree of freedom for U. Now blocks, we have 6 blocks and one factor which is coarser than that one. So we subtract the degrees of freedom for that factor from the number of levels, gives us a 5. And then here, for the equality factor, we have 2 factors that is coarser. So we add up the degrees of freedom for all the factors that are above in the diagram and subtract it from the number of levels. So we get here a 24. So that is done for the plot factors, and we could do a similar thing for the treatment factors to get the ANOVA. Likewise, we could calculate the sums of squares using the same procedure, but starting here with the crude sum of squares for the universal factor in this example, then subtract from the crude sum of squares for blocks, the crude sum of squares for u, which is equal to the sum of squares for u, and then we subtract from the crude sum of squares for the equality factor the sums of squares for u and for blocks to get the sum of squares for the equality factor. Now, the sort of structure that is required to actually do the analysis of variance involves now the specification of what structure we require for the plots. And that is what Rosenby calls an orthogonal plot structure. So we have a set of factors which are defined on the set of observational units. We require that it contains the universal and the equality factor. We also require that if we look at a particular factor in curly f, and we look at all its classes, then all those classes are of the same size. So that means, in other words, for each level of a plot factor, there is the same number of observational units which have that level. We also require that whenever f and g are in curly f, their infimum and their supremum is, and we require that any two factors in that set are orthogonal in the sense of Rosenby's definition. We have another definition that is now related to the treatment structure. So we have another set, and I should have here, sorry, a G. An orthogonal treatment structure is a set G of inequivalent factors now on the set of treatments, and that makes few requirements. So the universal factor needs to be included whenever two factors are in curly G, their supremum is, and all factors in curly G, if we look at two of them, they are orthogonal to each other. And finally, in order to actually be able to come up with the ANOVA, we need to define an orthogonal design. And an orthogonal design has, in Rosenby's theory, three components. It has an orthogonal plot structure, an orthogonal treatment structure, and then there's a design function T which actually allocates the treatments to the observational units, and that needs to satisfy three more properties. The first one says that if we now regard the treatment factors as factors on omega, so first apply T, and then this assigns a treatment to an observational unit, and then apply the treatment factor. If we do that, then for any two G1 and G2 in our set curly G, the factors regarded as factors on omega should remain orthogonal if the original factors were. Then we also have here that if we have the plot factor on omega and a treatment factor on T, then the plot factor is orthogonal to the composition G after T. So if we again regard G as a plot factor. And then the third condition here says if we have a plot factor and a treatment factor, then the supremum of any plot factor and the treatment factor regarded as a factor on omega needs to be a treatment factor itself. So if we have that, then we actually can get the ANOVA, and we assume a specific structure which is written down here. And I'm again not going into the details, I just mention here that we're assuming that all the plot factors have random effects, and because of that the covariance matrix of our response vector y has a specific form. And if we assume that, say, common structure, although from the notation it may not be obvious, then what is important to note is that the W spaces which appeared in the theorem about decomposition are now the eigenspaces of that covariance matrix, or what is called, they are the strata. And here's some more detail about this matrix, but because of the time, I'm not going into those details. And now we're almost through with this long quote. So if we have an orthogonal design as defined on one of the slides, then we may come up with the null analysis of variance. That only involves the plot factors and has a line for each plot factor, and we only put the degrees of freedom calculated as those d values we saw in the theorem about decomposition. Then, by adding in the sums of squares, again computed from the Hasse diagram for the plot factors, we expand these into calculations ignoring treatments. And then we also have the treatment factors. Now we come up with something which is called the skeleton ANOVA, and that shows within which stratum or for each treatment factor is tested in. So it allocates the treatment factors to the different strata, where the strata again are dependent only on the plot factors. And here is this theorem from Rosemary's book, which says, okay, if we have an orthogonal design and we look at any treatment factor, then there is a unique plot factor which is finer than the treatment factor and which is the coarsest of all plot factors that are finer than the treatment factor. And then we get the ANOVA. So write for the expectation part simply tau, and if we project it orthogonally on some one of the W spaces, write this, and then what we actually do is, or the way I describe here the ANOVA is, so we have such a stratum for each plot factor. So there will be several of those bits here, one for each of the plot factors. Within each plot factor, we do have several of the treatment factors. Now, the degrees of freedom here for the stratum, they come from the Hasse diagram for the plot factors of the null ANOVA. Those degrees of freedom here come from the Hasse diagram for the treatment structures. This sum of squares comes from the Hasse diagram for the plot factors, those from the diagram for the treatment factors, and then we obtain a line for residual, and then that is obtained by subtracting the sum of those from this one here. And then we can actually look at the expected mean squares to tell us how to do tests of the effects. And the important thing is that every effect here in a stratum is tested against the mean square for the residual in that particular stratum. Okay, so now, I'm spent perhaps too much time on that. Now, as I said, for our package, we're requiring only an Excel file. And what I'm assuming here is that I have certain factors. One is designated of the responsive available, and then other factors which have names, and some of which are plot factors, some of which are treatment factors, and they don't have to be in a particular order. Now, I assume that basically our biologist has been able to put in actually the columns, and just to illustrate how that would look like for our initial example. So 6 blocks of size 5, so we have a factor for blocks. Then we have here spray and pruning. Each spray is applied to 2 entire blocks, and then within each block we have here the pruning aside. You know that this is in systematic order and is not randomized, but that would not affect, of course, the calculations. Now, the program, the package, will then automatically deduce the approximate model and carry out the correct analysis. And what is the programming approach I've used? So, what I want to do is actually to implement Rosemary's approach literally. So, every procedure in the program refers to one of the specific results or definitions. And to this end, what I do work with are factors in terms of their classes. So I'm working with sets of sets. In particular, I do not employ any design matrices in the usual sense. I use Mathematica since it allows very flexible data structures and supports corresponding operations, for example, for sets. It provides a function for drawing the Hasse diagram from a partial order, which is quite convenient because trying to program that yourself is not so straightforward, at least for me. It can do symbolic and numerical computation and has many other desirable features. Now, what is basically the algorithm, the sketch of the algorithm? So think about this Excel file. Now, suppose I have specified plot factors and treatment factors, and I consider the treatment factors already as factors on omega, so after applying the design function t. So the first goal is f may contain several factors, but it may not contain all the infima and suprema. It may not be an orthogonal plot structure. So what I do in the first step is I will turn f into an orthogonal plot structure if possible. So how do I do that? I form the closure of f by including all suprema of pairs of factors in the original curly f and iterating this process until all the suprema and all the infima are included. I then check the uniformity of the factors in the new set curly f after including the suprema and infima. And I also, should mention, include u and e for plot structure. And then I check the orthogonality. So if all those tests are passed, then the 6 bits defining an orthogonal plot structure are satisfied. So this is then going to be an orthogonal plot structure. I turn G, the set of treatment factors, into an orthogonal treatment structure, regarding it, however, as a structure on omega. And for this, it is required that for any two factors in the set, the supremum is included and also u is included. And I do that by using a specific option minimal. But sometimes I may basically also wish to include all the infima and the equality factor on the treatments as well, so I have another option, maximal. Then I check orthogonality of the new set of treatment factors. So that is then an orthogonal plot structure. And I have to check orthogonality of the new sets f tilde and g tilde as one of the requirements for an orthogonal design. And finally, I must make sure that if I have any plot factor in curly f tilde and a treatment factor in curly g tilde, then the supremum must be a treatment factor. That is another requirement of an orthogonal design. So if some of those are not yet in, I put them into g tilde. And if f tilde and g tilde pass all those tests, I actually have an orthogonal design. So the analysis of variance is then based on using the final relation and the Hasse diagrams, and I print out my results in the form Rosemary does. And here, because still user-friendliness is an aim here, I have a single command. So the package provides a single command, automatic ANOVA. You specify the data set as an Excel file. You give a list of plot factors as column numbers. For instance, 1, 4, and 5 here in this example. 1, 4, and 5. A list of treatment factors and a response variable if available. And I specify minimal or maximal depending whether for the treatments I want to have a maximal model or a minimal model. So that's it. Examples. So because of the time, we will not be able to run through all the examples, but I mean, I have produced a handout, if you just can pass that around, for 2 of the examples so that you can compare what the program gives you with what is, for instance, in Rosemary's book. So I come back to the introductory example. And now here's the program. So that's a Mathematica. Now the first thing I do is actually tell just Mathematica where to look for files. And now I load my automatic ANOVA package. Now I have several examples. So here in the first section, they are all from Rosemary. Now the very first one is the side apple example. So I specify the Excel file. I say the first factor, that was 1 for the blocks, is a plot factor. 2 and 3 are treatment factors, and 4 is the response. For the treatments, I want the maximum model. So let's do it. So the program does a number of things. It checks whether the inputs are okay in some sense, so no missing data and stuff like that. Then it basically follows the stages of the algorithm I described, and then it gives us here the Hasse diagram for the plot factors, which is so simple here. And then it gives us the Hasse diagram for the treatment factors, which looks like that. So we have here spray, U, pruning, and the infimum of the two. That here is just a matter of printing, so pruning goes on to actually show here 5 and 4, but I have to deal with some of the graphics options just to properly show it. But then we get the ANOVA table. And that should be the same you see on the first page of the handout. Apart from that, I have also included p-values. Also, I've not talked about how actually the variance components are calculated, but they are, and I checked also for all those examples. For instance, I agree with what Jenstedt would give you. So that's one example. Next one, going back to the presentation, is an example Rosemary calls bean weevils. So we have, again, a field. This is divided into 6 rows and 6 columns. So these will be our plot factors. We have then 5 treatments, and these are allocated essentially to the plots 36 observational units by means of a Latin square, where one of the treatments gets 2 symbols in the 6 by 6 Latin square. And each of the numbers here for the treatments is again defined in terms of 3 factors. So what I put in then is actually a column for, in the Excel file, for rows, one for columns, one for type, one for pheromone, and one for neem oil. And then, again, now doing the, so we can basically fold the other stuff away. Sorry. So now we go to the bean weevils. Now the first 2 factors here for the plots are rows and columns. Then these are the other treatment factors. I don't have a response variable here, so what I will get is not a full analysis of variance. I will only get a skeleton ANOVA. So again, here is the Hasse diagram for the plot factors. We get a Hasse diagram for the treatment factors. And we get the skeleton ANOVA. And there are 2 things worth mentioning here. What you see, and that corresponds to the Hasse diagram here, the degrees of freedom for the infimum of pheromone and neem oil is equal to 0, and that shows up here, and this tells us that we cannot have a test for that later on. So that's one thing worth noting, and also the other thing worth noting here is because we do not have data, the program automatically generates those formulas here for estimating the variance components. Sometimes those are of interest to people. Okay, example number 3. again from Rosemary's book. I mean, one of the reasons why taking those examples from the book is they are qualitative, all of them are qualitatively different, and also it gives you an easy way of checking whether the program does what it should do. Now, we looking here at an experiment on washing cotton sheets. So we have 4 wash temperatures and 3 drying temperatures. So these are our treatment factors. We have 8 washing machines and 6 dryers. So how is that experiment carried out? 48 sheets are randomized to the 8 washing machines, 6 per machine. And then 4 of the 4 washing temperatures are randomly assigned to the machines. So each washing temperature is replicated twice. After washing, the 6 sheets from each machine are assigned to a different dryer. And then the 3 drying temperatures are randomly allocated to the 6 dryers again with replication 2. Now, again, folding away this example. Now here we have 1 and 3, those are for the plot factors, which are in this case here washing machine and dryer, and these are for the treatment factors, so that is washing temperature and drying temperature. Again, we do not have observations, so we get now here Hasse diagram for the plot factors, Hasse diagram for the treatment factors, and the skeleton ANOVA, and again those formulas for estimating the variance components. Okay. So the next example, that is again one for which you have the handout. That is the following here. So that's on the back. So Rosemary reports an experiment on beans. So we have 4 blocks. Each block is a 3x4 rectangle. We have 3 treatment factors with 3 levels: cultivar, 2 levels seeding, molybdenum, 2 levels. And then we call the rows of each block strips, each column of a block quarters, and we group within each block 2 columns into a half, so we have 2 halves per block. And this gives you an idea of how then the treatments are assigned to strips, halves, and also quarters. And now let's see what we get in this case. Oh, sorry, that is the wrong one. So the first 4 are for blocks, strips, quarters, and halves. First 4 variables in the Excel sheet. Sorry. And then the other one are for cultivar, seeding, and molybdenum. So now you see the Hasse diagram for the plots becomes more complicated. And also the one for the treatments becomes more complicated. And we get, again, this skeleton ANOVA. That's the same apart from the order of the strata that you have in your handout. And again, you see the formulas that are derived by the program for estimating the variance components can also become more complicated. And I mean, perhaps because of the time, I think refer to one additional example which illustrates where, a pseudo factor is automatically added. Now here, that is simple in a sense. So that's a rice field. We have divided it in 8 rows and 4 columns. and then pairs of adjacent rows are called blocks. And then we have only 8 unstructured treatments which are assigned to the intersections of blocks and columns, which are called cells as specified here. And now, when we do this, so that's the irrigated rice example. So we have here specified, what we specify here is actually plot factors as such. We say we have blocks, and we have columns, and we have cells, and we only specify a single treatment factor, the unstructured treatment factor, here column 4. Now if we run that, you see that is our diagram for the plot structure. That is for the treatment structure, particularly simple. Now you see here, we have here the supremum of cell and T, which was not in before. And that is what Rosemary discussed as a pseudo factor that needs to be added in this particular example. And this gives then here the skeleton ANOVA. And I mean, we would also have been able to omit cell, and the infimum of block and columns would be cell. That would also have been automatically added. Okay, so that's a quick demonstration of the program. I just want to perhaps finish off with a few future plans and one slide for discussion. So I want to put this on a web server. So there are mathematical tools for actually integrating this well on web pages so that anyone can use it easily. I also perhaps want to add a function which would automatically generate the corresponding Jenstedt syntax for the deduced models, perhaps add confidence intervals for variance components, and some imputation algorithms if there are some missing data. The discussion, the summary is, I hope I have given you an idea that Rosemary's theory is very powerful for dealing with a large number of models. But applying that in practice for a customer is often very time consuming. And I think for that reason, user-friendly packages such as the one I've presented will be helpful. My presentation here has been basically following the UK philosophy, talking about plot factors, treatment factors, but the program could equally well be used if you come from a model-based world where you talk about fixed and random effects. Then you would, for standard assumptions in this model-based world, just identify or define each random effects factor as a plot factor and each fixed effects factor as a treatment factor. And then you would basically get the correct analysis. There is a restrictive assumption here which does not allow to generalize that theory to generally arbitrary unbalanced, or designs with an arbitrary unbalanced plot structure, this uniformity thing. Here are the main references. So essentially I've used over and over Rosemary's book. There's another book which contains another example I have not talked about today because of the time, which goes beyond Nelda's simple orthogonal plot structures, and here are Nelda's original papers. And finally, if you have any examples, complicated ones, which you would like to share, I should be most grateful. Thank you.
Thank you very much indeed, Heiko. As far as I know, nobody else is pressing to get into the room, so it's time now for any questions or comments.
It's quite interesting to start out with just the factor information and deduce an ANOVA. I think it's a great idea. But you were a bit incorrect in one of your statements, and you said that Jenstedt's the only package that implements this sort of approach. Well, it's in S and R as well in the AOV function. Most people don't know about it, so you're right about what people don't know about and don't take up. But in fact, there's a thing called the error function in S plus and R. It goes right back to Chambers' original implementation. And if you put the plot structure in the error function and the treatment structure outside it, it divides it up by strata, and it works for non-orthogonal experiments as well as orthogonal experiments. So it will be possible to generate the same structure formula that you want to have in GenStat and put it into R, in the AOV function R, and generate the same analysis of variance.
Okay, thanks.
What it doesn't do is a dummy ANOVA. You have to, outside the function, generate a set of Y values, just randomly generate some Y's and feed it in, and then you get the dummy ANOVA sort of thing with a whole lot of dummy sums of squares.
You cannot handle the case with pseudo factor. You cannot handle the case with pseudo factor in R. I think if you create some pseudo factor, if your design creates some pseudo factor, you won't handle
I don't see, well, not sure, I have to think about it. Might be.
I think that if you perhaps would look at the books, the two books by Zalinsky and Kageyama, I don't know if you have.
I have, yes.
Did they not show some examples which would be useful for this?
I may go back to the books again. I mean, I have not got as deeply into those, say, two books.
But basically the ideas are very similar in these books. I also look at
yes, I believe
block
that,
structures. We don't use so much Hasse diagrams and this kind of notation which Rosemary does. But basically the structures of treatments and units are considered there in a similar way.
I mean, one of the points I'm trying to make here is that by just reading 30 pages in one book, you can get a clear understanding of what is going on. And then you can actually have an automatic version of this process which covers very many situations, which is practical. So,
Yes. But you ask for more examples.
Yeah, okay. I will go back to those, yes.
I was just going to say, I mean, I think there are lots of examples in there, but I think they don't have very complicated block structure ever, those two
Maybe, I
books, because
don't
they're basically
remember
about
now.
block design. Steve?
So, yeah, question about the input. So if there are nested factors, am I right in thinking, so if you've got F2 nested within F1, the levels of F2 have to be defined uniquely? You can't have
Yes.
one.
Yeah, otherwise the program would think you are dealing with a cross situation.
So that means a big warning stamp for
Yeah.
users.
Yes.
Well, I was wondering whether I needed to say that just now, because after this discussion from Chris and Piwen, so, for example, if you do this in R, if you had the cider apples thing, do you say that your tree factor has 5 levels or 30 levels? Because the way Heiko's doing it, it has to have 30 levels.
Well, I think you have to specify the block structure and
Yeah,
treatment structure, so you do it accordingly.
yeah.
I mean, I'm not explicitly specifying numbers of levels anywhere. They are just picked up from the columns, right? Yeah.
But for example, in your case, you didn't have to put in the trees, but supposing you'd had to, so you give the block numbers go like that, and then the tree numbers in your system, and the way I think about it as well, you have to have a separate number for each tree, whereas in some of the other systems that people are used to, you could put 1, 2, 3, 4, 5, 6.
Sure.
And then start again, but then you have to use a different syntax to explain it. So I think there is a possibility for confusion between those two approaches.
My other comment was CSS stands for crude sum of squares. I think I've seen CSS used for corrected sum of squares, which is exactly
I mean that is the usual issue about names. I have just used CSS because just actually to match Rosemary's notation, just to be consistent with that. But
If you've got better notation, I'm not
Do you
objecting.
provide help or something with explanation of what you do behind? in formulae or whatever,
No, what I'm trying to
or how to input the data.
yes, I
So these
mean
Excel files, people who are not that familiar with the theory, they need to know the
sure.
order of putting things.
Yes, I mean, one thing I do is because you can add part of such information as in the package. Sorry, just Nova. So there's a convention that you define something like usage, and then that tells you something about the package itself, what it does, and you could, of course, add more, and then you can also have the same thing for the function, and that would, in this case, I've just put in something which tells you what the arguments are, but you could put in more, and but of course, in addition to that, my plan is actually to write a paper about this approach, and so that would also discuss.
Yeah, but when people use it, they will not necessarily see your paper. So it's good. For example, if they use that and see the formulae for the various components, they will say,
Yeah.
well, what they actually are, and then if they find in help the explanation.
I mean, I have tried
would be useful.
to implement some things which should make the application foolproof, but there's more to do. For instance, if I repeated the same factor, the treatment and the plot factor, then the program would pick that up, and there are, you see here, and there are many other things which I have already implemented, which would prevent the user from doing things that are not intended. So they would, the first time the user makes a mistake, he would get a message basically telling, okay, don't do that, and then perhaps can correct his mistake and use the program properly next time.
Ever?
I'm just wondering, is there always a Hassett diagram, a global one for the treatment and plot factors, and is it trivial to find it, to have done the calculations?
No, I mean, the thing is, I mean, if you, for instance, just put together all the treatment factors and the plot factors, then there may not be a proper Hassett diagram, or if there is, then that is different from the one which you in general is different from the one that you obtain by piecing together the different ones. The step where you allocate the treatment factors to the strata, that is essentially the one where you could draw together the two diagrams, and Rosemary has given examples of that in her book, but I'm not sure how in general I would do that. And so I think probably it may be possible to join them somehow, but I mean, it becomes probably a big problem, a practical problem, where to put all the nodes and the edges, and I mean, at the moment I'm not worrying about that at all, because I let Mathematica take care of that for the Hassett diagrams. Yeah.
Heiko, you mentioned that you are going to work on imputation methods for missing data, but are you also going to do something about the unbalanced structure of nesting?
I mean, the thing here is, if we're talking about the treatment factors, they do not necessarily have to be balanced. The critical or the crucial point where the balance is required when we're talking about the plot factors. And what I seem to understand is that the theory entirely breaks down if we have to give up the assumption of uniformity, as it was called here, for the plot factors, because then in general, at least for the sort of covariance matrix we assume here, the W spaces for the plot factors are no longer the strata for the covariance matrix. So that I'm not sure whether I think there examples in the literature which show that it is not easy to try to rectify that problem, that it is not possible to rectify that problem.
Can you put your further work up again?
Yep.
Future director. I just want to ask anything, I just wanted to see. Confidence intervals for variance components, is that, I mean, in general, that's an almost impossibly difficult problem. Is it within the set of orthogonal design, is it not too bad?
No, that is only because, I mean, I have not explored that in detail, so I would probably have to resort to a book like Searle to get some idea. And at this stage, I would leave basically the non-model-based world to probably come up with those. I'm not sure. I have not really looked into it so far.
That would depend whether you are taking a variance components approach or a stratum variance approach. In other words, what you're insisting has to be positive.
It might be also interesting to think about efficiencies in strata or estimation, maybe of interest.
Yeah.
That may be actually not too difficult to do that.
Yeah, I mean, there are probably many other directions
Yes,
one
yes.
could go into, but I mean, to, in a way, reach a point where you can say, okay, now I have achieved some goal, so I think I want to declare
I think
the
you've
first
got a
part of
tool
it.
which you can develop for many years.
I've got another suggestion. Since people who are using GenStat or ANOVA probably more or less know what they're doing anyway, should you think about automatic generation of syntax for SAS? For people who don't know what they're doing.
Is that being recorded?
Yeah, I mean, of course, that's another possibility. Yeah, but I mean, in a sense, these are purely, say, computer science problem, converting one syntax into another one. So.
Yeah, except that the way you're thinking about it naturally fits in with the GenStat syntax. Perhaps more than it actually fits in with the SAS syntax.
Yeah. No, I mean, that would be interesting, of course, but yeah. But yeah, sure, that is something that could be done.
The other thing that did make me shudder a bit when you said you could do mixed models by changing what you're calling block and treatment into fixed and random. Do you know that you can use the Hasse diagrams to generate expected mean squares or arbitrary designation of fixed and random factors in both the Hasse diagrams? It'll certainly work for orthogonal design.
Yeah, I mean, that is basically underlying how I estimate the variance components.
Yeah, so what I'm suggesting is that if you want to have arbitrary models, I think the way I would ideally think you might go about this is to say you have another specification that says these columns correspond to fixed factors and these correspond to random, so you've got to have another two sets and then use the Hasse diagrams to work out what the expected mean squares are for that specification. Rather than saying change the block and treatment, you have to introduce a further classification basically, which is into fixed and random.
On top of what we already have. Or
Yeah.
Yes. So, for example, I mean, I was going to say that you could have treatment factors which are random.
Yep.
Yes.
And you can have block factors which are fixed. And so...
Sure, but I mean, that would not basically, I think, affect, you would get the same covariance matrix.
Yeah.
And then basically the analysis would be the same, and you could after. So at the point, what I was trying to say is at the point where I try to label or use the treatment factors for all fixed effects, one after getting the analysis, one would again match perhaps a fixed factor which was in fact a plot factor back or in the interpretation. Because I mean, if you write down the model in terms of y ij is equal to sum of whatever, and then you look and assume that all the random effects have a mean of 0, and look at the variance covariance matrix, and the standard assumption would probably be, I think, the same that I've assumed here. And then the ANOVA would be the same.
Random treatment effects, you might be interested in the interaction of them with a fixed treatment effect.
Which would be pseudo factor. I mean, it would come up.
Because your pseudo factors are the suprema and the interactions.
Not necessarily. I mean, pseudo.
Oh yes, because if you put in that model that you do want it closed downwards, yeah.
Yeah.
Okay.
But I mean, in general, of course, that is an interesting suggestion to see what cases there are where the introduction of a separate set of fixed and random effects could be done here, or what the consequences.
I mean, it's kind of tricky because what you no longer have what you call strata are no longer strata, because if you've got a random factor that's fixed, then you've got an eigenvalue. Well, that factor has a subspace that's not an eigenvalue of it's part of an eigenvalue of the covariance matrix. So it sort of gets, it's not decomposed according to strata anymore. But the analysis is, the decomposition's still right, but it's not, doesn't fit into the nice theory.
My theory isn't nice enough. Thank you, Chris.
No, I just want to mess it up a bit.
Yeah. So Heiko, it seems to me that you've generated a lot of interest. I mean, and thank you very much for your nice tutorial on my book. But quite apart from that, I think this is just amazing. We know that biologists come to us with Excel spreadsheets, and your simple command that you've shown us, that it can produce all of this. Okay, so it doesn't do non-orthogonal designs with efficiency factors. It doesn't do things where you might want to mess up what's random and what's fixed, and it can't do unbalanced random factors, and there are good reasons for that. But the fact that with that one command, you can do a lot of the things that people actually use in practice, and as you say, maybe for people who certainly can't read 30 pages of my book. I think that's great, and I hope you'll develop it further. And all the people who've been here and have listened and have made comments, I do hope you'll continue the interaction with Heiko, give him examples, and discuss further the things that we've talked about today. So thank you very much indeed, Heiko.